Now you know how force affects objects themselves and not just their motion, right? And you know how to use the expression for stress and strain to quantify this effect? But is there a way to quantify the difference in how objects react to forces? Can we, for example, show how one object is more elastic than another? Or that one object is more brittle than another? Now, one way to visually represent how materials react to forces applied is to draw up their stress strain graph. And just a quick recap, stress is the force per unit area applied to the material, while strain is the resulting deformation of the material. Now, the process here is simple. We apply a force on an object and use that to determine the stress on it. Then, we measure the deformation cost and use that to determine the strain on the object. Now, once we've measured stress and strain at different points, we can plot a graph to show the slope of the linear region. Now, usually this process is repeated for a sample until it breaks, and that gives us a complete profile of the material's behavior. Now, when we look at the final graph, we'll see a portion that's a straight line. This portion represents the stress and strain on the material within its limit of proportionality. So, basically, it's the part where Hooke's law applies. As we increase the force, that is the stress, the extension or the strain also increases. But when we remove the stress, the spring goes back to its original shape and size. So the relationship between force and extension, that is stress and strain, is linear within any material's limit of proportionality. The slope of this linear part of the stress-strain graph gives us the material's Young's modulus, which is also known as the modulus of elasticity. At its core, it's a measure of the stiffness of a material. It's basically a constant that relates the stress applied to a material to the resulting strain. Think of it as a measure of how much a material will stretch or compress under a given stress. And that rhymes, so it should be easy to remember. Anywho, we can calculate Young's modulus by dividing the stress on the object with the strain. This simplifies to give us this expression, where F is the force applied, A is the area of contact, X is the extension cost, and L is the total length of the material. Now, since Young's modulus is a measure of stiffness, we can visibly see which material is stiffer using the stress-strain graph. So, for example, steel will have a much higher Young's modulus when compared to rubber. That is, it'll take much more stress to produce the same amount of strain in steel. So on the stress-strain graph, steel will have a much higher slope as compared to rubber. But what about beyond the elastic limit? What does the stress-strain graph look like when it crosses the elastic limit? And what does that tell us about the material's behavior? Let's try to understand that using steel as an example. Let's say you're in your lab trying to determine the behavior of steel using a stress-strain graph. You take a steel wire, suspend it from a fixed point, and attach a weight to the bottom. Now in this experiment, you'll basically add weight at different intervals, and as the weight pulls down the wire, it stretches, and you measure the extension. And here's how you do that. You start off by measuring the diameter of the wire with a micrometer screw gauge. After that, you'll set up the experiment, measure the original length of the wire using a meter rule, and then mark a reference point on the wire using something like tape. Now, record the initial reading on the ruler up to the reference point. Now you're going to add another weight and record the reading. Great. Now it's simple. Just repeat this process, adding in more and more weights and recording the new readings. By doing this, you can determine the stress and strain at each interval, and you can use that to plot a stress-strain graph. Here's a table with some sample results. Starting out with a mass of 200 grams, we kept 100 gram increments up until the net mass reaches 800 grams. Throughout this process, we measured the net force and extension at each increment and tabulated them for you here. Next, we plot the force extension graph and then calculate the gradient. We've talked about the formula for Young's modulus earlier, that is, force multiplied by length divided by cross-sectional area multiplied by extension, and we're going to use that formula to calculate the Young's modulus for this set of results. And that's where the gradient we just calculated earlier comes into play, because it's basically calculating force divided by extension, right? So we plug that in and we have the length and cross-sectional area. Initially, you'll notice that the graph is straight. And this makes sense because within the limit of proportionality, the stress strain relationship will be linear. But as you get to the elastic limit, the same amount of stress will increase the strain by a lot more. And you'll be able to see this because the graph will start to flatten a little. Now, there will be a point after which the graph will no longer be linear. And this is called the limit of proportionality. As you add more weight, you will reach the elastic limit, after which the material will permanently deform and not return to its original length. Now you keep adding weight. There will come a point when the wire reaches its ultimate tensile strength, which is the point where the wire loses its strength, extends, and becomes narrower at its weakest point. The wire will soon break now, and this breaking point is called the breaking stress. Great! Now that you've done this with steel, you know all you need to know how steel behaves at different stress levels. And you can plot these graphs for other materials as well and compare how they behave in different situations. So for example, glass will have a curve that looks like this, which shows that it's brittle and will break instead of going through plastic flow. So it takes the phrase "over my dead body" a little bit too seriously. Copper would look something like this, showing that it's very ductile and malleable, which means it'll deform a lot under very little strain. And that's why it's so much easier to roll into wires. Now let's say you're comparing just these three. Just that simple comparison can tell us that steel has a much higher ultimate tensile stress, which basically means that it's the strongest of the three. These comparisons are so important, especially when it comes to designing things that use these materials as components. And that could be a building, it could be a bridge, it could be a phone, it could be a car, anything. But when you know the limits of the materials you're using, you can design things that don't fall apart because of a single weak point. And believe it or not, that's pretty important. So, I hope you paid attention. And until next time, ciao.